When you think about glass, what is the first thing that usually comes to mind? A drinking glass? Or maybe the windows in our homes and cities? We usually picture something clear, fragile, even delicate. But what if I told you that glass could also be something strong and dense enough to support the ground you stand on? This is possible due to vitrification, a ground improvement technique that doesn't just stabilize the soil, but transforms it into a solid glass-like mass. Now when we say glass-like, we're not talking about how it looks. We're talking about its internal structure. Crystalline materials like salt or quartz have neatly ordered atomic lattices. Liquids, on the other hand, are completely disordered and free-flowing. Glass is unique. It's a solid, but its atoms are arranged like a liquid. This gives it both rigidity and chemical stability. So how does vitrification turn soil into a material with that kind of structure? By inserting electrodes into the ground and passing powerful electric currents through them, we heat the soil to extreme temperatures, typically over 1600 degrees Celsius. That's hotter than lava, which flows between 700 and 1200 degrees Celsius, and even hotter than the melting point of steel, which sits at around 1500 degrees. At this point, the minerals melt, and as the soil cools, it solidifies into a hard and impermeable glass-like block. This process doesn't just improve soil strength, it also acts as a long-term environmental barrier, permanently trapping hazardous contaminants such as heavy metals, radioactive waste, or industrial chemicals. By turning them into a part of a solid glass-like matrix, vitrification prevents these substances from leaching into groundwater, spreading through soil, or reaching surrounding ecosystems. So how is vitrification planned and designed for a specific site? It involves several steps. First, engineers conduct geotechnical and chemical analyses to understand the soil composition and contaminant profile. Then, electrodes, often graphite or metal, are arranged in the grid pattern and the fume hood is placed over the soon-to-be vitrified soil. This traps gases which can then be captured for treatment. When the vitrification process starts, real-time monitoring is essential. Sensors are used to track temperature gradients, energy consumption, gas emissions, and soil resistivity. This allows engineers to make live adjustments, ensuring complete vitrification and that the surrounding soil or structures aren't unintentionally affected. There are also safety protocols to manage potential off-gassing, which could include trace amounts of dangerous contaminants. Key design considerations include, first, the soil type, where silty and clayey soils with sufficient mineral content is preferred. Second is the moisture and contaminant content of the soil. Low moisture soils are preferred since water must be evaporated before vitrification can begin, which adds energy cost and time. Third is the thermal conductivity of the soil, which determines the type of heat containment needed. Fourth and last is the size of the treated area, which will determine the number and placement of the electrodes as well as the needed power to electrify them. How does vitrification compare to other ground improvement methods like grouting and soil compaction? Like chemical grouting, it improves strength and impermeability. On the other hand, like deep soil mixing, it is used for environmental containment. While those methods rely on mechanical or chemical means, vitrification uses extreme heating, which allows for it to permanently immobilize hazardous materials, whereas the other methods may just contain or dilute them. The high cost and complexity involved with vitrification is the reason why it is not used for routine geotechnical improvement. Ideally, it is only chosen for sites with high-risk contamination, where alternative methods such as manually handling the materials for off-site storage becomes more costly over time, aside from the possible risks faced by workers by handling these materials. Some notable examples of vitrification is its use in the Hanford nuclear site in Washington, where radioactive waste is currently being vitrified and placed into stainless steel containment vessels to be transported and safely stored in a federal repository. As of now, roughly 212,000 cubic meters of waste still await processing. Vitrification is also used in Superfund sites, where you can find the United States' most contaminated land. One such location is the Parsons Chemical Superfund site, a former agricultural chemicals mixing, manufacturing, and packaging facility. After about 34 years of operations, the land at the site was left severely contaminated with pesticides, heavy metals, and dioxins. Vitrification was used to reduce the contaminated soil volume by up to 30%, while also bringing the readable soil contamination and emissions to acceptable levels. While the United States has led much of the large-scale implementation of vitrification as mentioned in the previous cases, other countries like France, Russia, and Japan have also explored or used vitrification in the management of nuclear waste. In France, vitrification has been part of the national radioactive waste strategy since the 1970s. The process is chosen for its ability to dramatically reduce waste volume and the long-term hazards of the material, even if the upfront cost is high. While vitrification is a proven method for dealing with hazardous soil, there's still room for innovation. One of the challenges with vitrification is scalability. The use of graphite or steel electrodes have limitations. That is why plasma is proposed as an alternative, which can heat soil up to 7,000 degrees. The process involves lowering a plasma torch down a cased hole and initiating bottom-up column fusion. Theoretically, it allows vitrification to be done at any depth with incredible precision, allowing the treatment of contaminated hotspots without excavating large areas. However, even if the process has been demonstrated, it has yet to be widely used and commercialized. If plasma vitrification is explored further and becomes more energy efficient, it would be possible to see a broader use for it in the future. While vitrification isn't the most common solution, it stands strong when the stakes are highest. We often say we want our safety to be set in stone, but sometimes, to truly protect our lives, it needs to be set in glass.